Now we can continue our morning session. Our second speaker is Ivan Corwin, and we'll speak about something related to the Carter precision universality class, and will be probably the last plenary talk about this related subject. So.
Thank you very much. So as Patrick said, this hopefully will be the last you hear ever in the plenary lectures of KPC. In fact, KPC doesn't come up in my title. It will feature in a small way, but it won't be necessarily the main point. So I'm going to trick everyone. They thought I was going to stand over there. I'll stand over here. No, I'll move around. So this will be a talk about what I would call integrable probabilistic systems, which is a different perspective on studying KP's universality class than, for instance, what you heard about from Martin, and also different in a sense than what Scott was talking about. So for me, an integral probabilistic system, and this is a very rough definition, has two main properties. So the first property is that it should be possible to find a variety of observables of this system, of the random system, whose expectations are given via concise and nice exact formulas. So I'll be dealing in the realm of exact formulas. And the second property, which is a little different than traditional integrable systems, is that one wants that the limits of the systems, the limits of the observables, and the limits of the formulas should be, by taking asymptotics, give you access to very detailed descriptions of broad universality classes. So classes of models that contain more than just these special integrable points, however, instead are generally non-integrable. So you should gain information. So the simplest example of this, which is familiar to everyone, goes back a few hundred years to the work of de Moivre and Laplace, which is the study of Bernoulli coin flips. For that case, you can write down probabilities concisely as binomial coefficients, and then the use of Stirling's formula gives you access to the first instance of the famous Gaussian distribution. It wasn't until about 150 years later, work of Lyapunov and others, that people proved the universality of this distribution. So from the start, by studying an integrable example, you gain information about what should be a much larger universality class. So I'll focus on the integrable side of things. In particular, I'm going to focus mainly on models related to the Cardar-Grésy-Zhang universality class, something that we've seen throughout this Congress so far. And the source of integrability, which is what I'll emphasize in the second part of my talk, will come from connections to algebraic structures, in particular to representation theory and to integrable systems. So I want to start, however, by describing one model which will be pervasive throughout the entire talk. I'll keep coming back to this one model. And it's a model for one-dimensional traffic flow. And what we'll see is the reason why this is a nice integrable model is because there exists this family of observables which admit very simple expressions for their expectations. So this is a model called QTASAP. We introduced it a few years ago with Alexei Borodin. And you should think of it as particles or cars moving on a one-dimensional lattice, Z. And it's a continuous time Markov process, an interacting particle system. Cars jump, or particles jump to the right by 1 at a rate which is mitigated by the distance to the next particle, or the gap. The way that that's mitigated is it's given by 1 minus q. Q is a number fixed between 0 and 1, raised to the gap. The effect of this is that when the gap goes to 0, the rate goes to 0. You slow down, you stop. And when the gap goes to infinity, the rate approaches the kind of steady state of 1. Of course, q controls the length scale on which this transition occurs. Taking q very close to 1, or particularly equal to 1, results in particles that just jump until the moment they're going to hit the next particle, and then they just don't make that jump. And that's called the totally asymmetric simple exclusion process. So as I was driving over here from the airport, I was trying to measure what q was in my taxi ride, and unfortunately it was very, very low. So different countries have different values of q. So I'm going to consider indexing particles. X1 will represent the first particle, X2 second, and so on. I'll assume that there is a first particle. And in particular, I'm going to focus on an initial configuration which I'll call step, which means that there is essentially an infinite number of particles on the left-hand side and no particles on the right. So initially, xi for I positive is in position minus I. It's like a traffic jam, and you're looking at the rarefaction of the traffic jam over time. So the central theorem, of which I will give you two ways to prove, and then I'll also provide you with a number of implications, is that it is possible to compute a variety of exact formulas corresponding to this step initial condition, qk sub. So let me focus on looking at the nth particle, so the nth car, at time t. So I'm going to look at xn of t, and then I'll add in plus n, and this just suffices to kind of shift given the initial data. Now, rather than looking at the distribution of that directly, I'm going to be a little crafty, and we'll see why later. And I'm going to look at q, the same parameter q as in the process, raised to that number, raised to that random variable. And in fact, I'll look not just at that, I'll look at products of these as n variables. So I could have n1, n2, n3, and they can vary, well, they only need to be weakly ordered. So this is a weak order, n1 bigger than or equal to 2, and so on. Now the claim is that for this observable, if I evolve the system from step initial condition, I look at the expectation of these observables, I get a very nice, concise formula, which is, if I'm looking at k of these observables, it's given by a k-fold contour integral. The variables of integration are z1 through zk. The t and the n only come into the exponent in this multiplicative term. And otherwise, it's a rather simple form. There is what I would call a van der Waals determinant divided by a q-deformed van der Waals determinant, the product a less than b, z minus q zb. And then there's this purely multiplicative term, and then the dz over z. And because of the nature of this denominator, the za minus q zb, it is necessary to avoid certain poles that you get when the z's are equal. And this actually requires that you take a certain type of nested contour. The choice of contours must respect a certain nesting. Okay, so what good is this formula? Of course, where is the formula coming from will be the content of the second part of the talk. I want to start by telling you what good is this formula. So the first observation is that xn of t plus n is always positive, right? Because initially you start in position minus n, and so you always move to the right. So we're looking at q raised to a positive number. That's a random variable which is bounded between 0 and 1. So the knowledge of all of the moments, or all of the joint moments of these random variables, uniquely characterizes the distribution. So in principle, by knowing all of these formulas, we actually know the entire distribution at time t of the system. That's not to say that we know how to extract any meaningful information from these formulas. This just characterizes it. So the real challenge from the start will be, given these formulas, how do we extract meaningful information, especially asymptotic information, so as to be able to predict what happens as n and t and perhaps q's all scale. So let me focus for one moment on an application of this. So imagine, for simplicity, take all of the n's to be identically equal to capital N. So rather than looking at joint moments, we're looking at a very simple observable. We're looking at q to the xn of t plus n, and we're looking at its kth moment. In principle, the knowledge of all of the moments of this observable will identify its distribution. Now, here I've just rewritten the formula. The idea now is that one wants to form a suitable generating function of these moments. Of course, any generating function will, in principle, contain the distribution. However, not every generating function will be amenable to asymptotics or will yield a particularly nice formula. However, there is one which is well adapted, which I'll describe, which is called the Q-Laplace transform. It's a simple deformation of the traditional Laplace transform of a positive random variable. And the way that it's defined is that if you have a random variable, q to the xn plus n, q to the xn plus n, you essentially take the expectation of a certain reciprocal infinite product. Now, this doesn't look very much like an exponential, does it? Well, it is an exponential. It was introduced by Hahn in 1949, and just like the usual exponential, it admits a very simple Taylor series. And the Taylor series is where the moment generating function comes in. So the Taylor series, or the Q binomial theorem, says that this Q exponential can be expanded as a summation k equals 0 to infinity of the argument to the kth power divided by something which, with a little bit of imagination, looks like a k factorial, or up to a constant looks like a k factorial. So in fact, this is a very good approximation for an exponential, and as q goes to 1, it becomes essentially such. Now, how do I use the formula which I've been describing in this? Well, the observation is that I can now interchange the expectation and the infinite summation. And now I'm taking a generating function of moments. Okay? There is still work to be done. So these moments, so now I'm going to bring the expectation inside. The moments are somewhat complicated. They involve complicated integrals over nested contours which get more and more complicated as k grows. Now there's a mantra here which one appeals to, which is that in general, when you have a sequence of integrals or a sequence of operators, and the spaces or the contours are growing in complexity, one should always try to move the complexity of contours and spaces onto complexities of integrands and kernels. And then this generally admits better asymptotics. So what you can do, and I'm not going to go through it, is you can essentially shrink all of these nested contours to a small circle around 1. And as you do that, you end up with a certain residue expansion of these integrals. And these turn out to actually organize themselves in a very nice way as what's called a Fredholm determinant. So in the end, in the end, you get an expression for this Q Laplace transform in terms of a Fredholm determinant. Now, just like the usual Laplace transform, you can very simply invert a Q Laplace transform via a single contour integral in the spectral variable, in the variable zeta. So this actually yields an expression which is, at this point, quite amenable to asymptotics, and I'll explain some applications in a moment. There is one point I want to make before I go on, though, which is that you should have had a little bell ring in your head. When I said interchange expectation and the summation, you should always think, can you actually do that? And in this case, it's perfectly fine, because even though this is an infinite summation, the random variable inside is deterministically bounded by 1. So as long as zeta is sufficiently small, you actually have a deterministically absolutely convergent series. Then you can do an interchange of this type. In a moment, we'll see an example where this fails. Okay, so I want to describe now a few limits of Q-Tesa, interesting ones, which ultimately will relate us back to the famous ABC equation. So the first limit which I'll describe involves taking Q to 1. So what happens as Q goes to 1? As Q goes to 1, the length scale on which the transition, particles can start to jump, grows. It grows like something like 1 over log of Q, or maybe with a minus sign. So the first particle, he always jumps at rate 1, so he moves freely. The second particle, however, needs to wait for the first particle to move far enough away before he can start to jump. And so what you end up with is a picture where the first particle has run away, and the second particle eventually lags behind him with a certain characteristic length scale, and then the third particle lags with yet another length scale. And over time, these particles, they're all moving to the right, but they kind of fluctuate, but within their own little mesoscopic length scale. Now, if you were to take all of these fluctuations and put them back onto a single scale, so now you've kind of removed the mesoscopic spacing, you end up with a continuous space version of Q-Tesa. A version, because we've removed this mesoscopic scaling, in which particles can really move through each other now, because moving through each other is not a problem, because there really was this thing I removed. And the interaction is that if the ith particle has moved past the I minus first particle, he feels an exponential drift to get back in order. So it's essentially particles moving according to Brownian motion with exponential drifts from going out of order. This is the limit as Q goes to 1 under some special scalings. Now that process, if one exponentiates it, leads you to something called the semi-discrete stochastic heat equation, which is equivalent via the Feynman-Katz representation to something which is known as the O'Connell-Yor semi-discrete Brownian polymer. So let me introduce that polymer. Of course, there was a little bit of a gap, which I tried to fill in, but one needs to think a little bit to fully understand the connection to Q-tesa. So this polymer, this ZNT, this should be thought of in a sense as the limit of Q to the xn of t plus n. Okay, so this was the exponentiation that I did to the continuum version of Q-tesa is akin to taking Q to the xn of t plus n. Now in this semi-discrete polymer model, what you consider is the following. You consider a collection of independent Brownian motions on levels 1 through n, and you consider a trajectory, or red curve, which moves along, starts at level 1, jumps up to level 2, to level 3, and all the way ends at level n. And as it moves along, it eats up the Brownian motion, actually eats up the white noise, and it accrues an energy. The energy is given by either the sum of the Brownian increments from each level, or you can think of it as the path integral along the trajectory of white noises given by the derivative of these Brownian motions. To that energy, we associate a Boltzmann weight, which is the exponential, and then we form a partition function, which is the sum over all possible red trajectories, over, in other words, the simplex of jumping times S1 through Sn minus 1 of the Boltzmann weight. So this is the partition function for a directed polymer model, in which one then describes a measure on these paths. I'm only going to focus, however, on the partition function itself. Because of the connection between Q-tesa and this polymer model, one gets that the Q Laplace transform, as Q goes to 1, becomes the Laplace transform of this partition function. Of course, the Laplace transform of a positive random variable also identifies its distribution, and this allows you to perform certain asymptotics. So I'll record one asymptotic result, which is that if you look at the logarithm of z, which essentially brings you back to the level of a continuum version of Q-tesa, and you scale both t and n to infinity, so you look kind of in a diagonal direction with a ratio kappa between them, then the fluctuations of this free energy or of this sort of continuum Q-tesa particle behave deterministically like a constant times n, and then fluctuate in the order of n to the 1/3 around that, with a limiting distribution given by the Tracy-Whittam GUE distribution, something which first arose in the context of random matrix theory, describing asymptotically large eigenvalues of the first fluctuation of the first eigenvalue. There is, of course, a result of this same sort for Q-tesa. If you look at the nth particle and time t, and you let both of them scale to infinity, and you keep Q fixed, you get a similar result. And this was proved by Patrick Ferrari and Don Vetto recently as well. There was a talk yesterday about that. Now, let's say that from the start you were only interested in this model, which I think is preposterous. You should be interested in Q-tesa. If you were only interested in this model, one might ask, is it possible to do the same sort of thing that I described? Is it possible to first study the moments of z, and then use those to recover the distribution? And it is possible to compute moment formulas. In fact, they are just limits of the moment formulas which I was describing before. However, the moments grow very fast. They're no longer bounded. In fact, because the Q to the xn of t, the convergence to this ZNT, is after moving something off, after dividing by something that goes to 0. So in the end, the moments actually grow far too fast to identify the Laplace transform and really to identify the distribution. I'll give you a very simple way of understanding this. Take the case of n equals 1. When n equals 1, all you're doing is looking at e to a Brownian motion. That's called a log normal distribution. And that's perhaps the most famous distribution for which the moment problem is ill-posed. The moments do not identify the distribution. So this is a kind of a more complicated version of that, but of course the same holds true. Okay. I want to describe one further limit, and then I'll start to get into the meat of how one actually finds these types of formulas, which corresponds to the following. So think of this path, this sawtooth path, this red path. Think of that as a trajectory of some sort of Poisson jump process. It's kind of moving, and it jumps up, and moves, jumps up. Of course, there is a simple way to scale that to a Brownian bridge. And you take time, think about time now almost as in the diagonal direction. Scale that, let's say, like epsilon to the minus 2, and then scale the fluctuations in the sort of diagonal direction, the anti-diagonal direction, scale that like epsilon to minus 1, and the red path will become a Brownian motion. However, as you do this, you find that you're kind of smushing together all of these one-dimensional white noises. All of the noise at each level gets smushed together. And in order that that noise itself has a limit, one needs to scale the noise down. Otherwise, the amount of noise per unit area just blows up. So the natural thing to do is to take what I would call a weak noise limit of the model, which involves putting a parameter, let's call it beta, in front of all of the Brownian motions, and then take beta to 0 in a suitable way as I take epsilon to 0. The right way is to actually take it to be epsilon to the 1/2. So epsilon to minus 2, epsilon to minus 1, and epsilon to the 1/2 for the noise. Now if you do that, you converge to what's called the continuum polymer partition function, which I'll be slightly informal in writing it. You can think of it, it requires a little bit of regularization to actually make sense exactly of this, but you can think of it as looking at a Brownian bridge, started at the origin, ending up at Tx, moving through a space-time white noise field. So these independent Brownian motions that were the underlying noise of the semi-discrete polymer in the limit become a two-dimensional white noise. Now, as you move along, you eat up the white noise, and this is, of course, what requires a little bit of sense. And then you exponentiate the energy of the given path, and you sum or average over all possible Brownian paths. Okay. This defines for you a function. It's a function of the endpoint, t and x. It's, of course, random because eta, my white noise, is random. And with a little bit of thought, you see that this is essentially equivalent to solving the stochastic heat equation, the multiplicative stochastic heat equation, by a Feynman-Katz representation with delta function initial data. So the initial data corresponding to the fact that my path actually starts off at the origin. Okay. This is, if you take its logarithm, this is what we've all seen over the course of these few lectures as the KPZ equation. And in fact, this is what is called the Hopf-Kohl solution to the KPZ equation. It is simply the logarithm of the stochastic heat equation. The initial data here is well, perhaps slightly degenerate when you think about taking the log of a delta function, but for any positive time, it makes perfect sense. This is what's called the narrow wedge initial data. I believe Kamahira spoke about this as well. Now, you can use the fact that we know the Laplace transform of the semi-discrete polymer under this weak noise scaling. That, of course, will become the Laplace transform of the continuum polymer, or in other words, the stochastic heat equation. And one can use this to rigorously prove the asymptotic, well, first to compute the distribution of the KPZ equation, the one-point distribution, and then with a little bit more work to extract the fact that asymptotically the KPZ equation has t to the 1/3 fluctuations in one-point distribution and has the GUE statistics. And this provides yet another rigorous way to prove this, the first being with Katie Amir, myself, and Jeremy Postel, as well as some non-rigorous methods that have been used. Okay, so this all fits into a certain wave of research, which I'll very briefly review, and then I'm going to explain where we sit in this. Okay? So this idea of studying exact quantities, exact formulas, and using this to extract asymptotic information about KPZ universality class, models which all share this same behavior. The first results go back to Kardar, Preze, and Zhang, or even earlier, Forrester, Nelson, and Stevens within the physics literature. And there they made predictions about the scaling exponents, in particular this 1/3 exponent. In the early 90s, physicists did a lot of numerics to try to get information about the distribution of the fluctuation. This was a hot topic. However, they never had any sort of explicit formulas, any sort of analytic results about this. The first results, and this is unusual, came in mathematics. So the first, the breakthrough was actually within mathematics. And it occurred in the late 90s with work of Beitek and Johansson. And this had to do with models that I'll call totally asymmetric or zero temperature models. You may have heard of the PNG model, the longest increasing subsequence, TASAP, last passage percolation. These were all models which essentially were solvable, as one understood soon after, via methods of determinantal point processes. So this meant that one could compute quantities, you could compute correlation functions for these point processes in terms of Miner's determinants of a single correlation matrix. From that structure, it became rather standard to extract asymptotic information, and this actually yielded all sorts of information about the KPZ universality class over time. So this would be what I would call Schur processes, for instance. Now, it also became clear that this determinantal structure was limited. It only applied to a few models. In particular, it didn't apply to the KPZ equation itself. In particular, it didn't apply to a model called asymmetric simple exclusion and various other models, QK-SAP being another example. So one of the revolutions in the more recent times of the late 2000s, first decade of 2000s, started with the work of Tracy and Whittam, in which they broke through this determinantal barrier. And they started to study a positive temperature, or in fact, a partially asymmetric model, and this was ASAP, asymmetric simple exclusion. And since then, we've developed a variety of techniques, algebraic techniques, beyond the determinantal structure. And so what I'll explain to you over the course of this talk is some of those techniques. Now, the techniques that I'm going to explain will be very exact or integrable in their nature. There are, in a sense, non-integrable or more probabilistic approaches. They don't give you as much detailed information. They don't give you distributional information, but they're very good, for instance, for computing scaling exponents. And so this goes under the realm of work that was started with Gronenboom, Hopdorf, Pimentel, Sepalainen, Valsko, Ballas, and others. I'm not going to go into those directions. This is a short picture, as well as a variety of names, associated with the non-determinantal models, the new models, which have been analyzed in the past few years. I've only focused on QK-SAP and then this degeneration to this semi-discrete polymer and KPZ equation. In fact, all of these models are supposed to, and in many cases have been proved to, converge to the so-called KPZ fixed point that I believe Martin talked about in his talk. This should be the limit of all of these models. In fact, it should be a limit of a much wider class of models. The arrows which are shown here actually refer generally to special scalings. So generically, if you fix Q and QK-SAP and you take a limit, you just get to the fixed point. It's only under the special Q goes to one limit and various other things, or for the semi-discrete polymer, only under the special weak noise scaling that you get to the KPZ equation itself. So the real big object is the KPZ fixed point. But one wants to understand a variety of models in the class because it allows you to both refine and expand your understanding of the universality class. Oh. So where did the formulas come from? I showed you one nice exact formula, and I showed you a little bit of what you can do with this formula. But where did the formula come from? And it didn't come out of thin air. There are two structures, or two sources, algebraic in their nature, which give rise to this type of formula, this type of result. And I'm going to give you a brief explanation of both of these approaches. It will be brief and in some sense incomplete, but hopefully it will at least give you a taste of what's going on. So one source is representation theory, and in particular the theory of symmetric functions. This is a source that's been used, for instance, starting in the beginning of this story, in the late 90s, early 2000s, in the case of Schur processes and Schur measure. We've upgraded it a little bit, and I'll explain the upgrade to the level of McDonald processes and what this gives. The other source is integrable systems, in particular quantum integrable systems. And again, quantum integrable systems have been intimately related to probability for quite some time. Two-dimensional lattice models, for instance, all fit into this structure. I'm going to explain a slightly different twist on this, in which one looks for these quantum integrable systems with stochastic transfer matrices and uses various tools that we've developed to study this. All of these ultimately yield integral probabilistic systems and tools to study them. Okay. So let me start by explaining a little bit about McDonald processes, and it'll be an overview. So McDonald polynomials are symmetric polynomials of arbitrary number of variables. Symmetric meaning that if you interchange any of the variables, the polynomial remains the same. And they have coefficients which are rational functions of two auxiliary parameters, q and t. These polynomials play a very special role in representation theory. They're really a high point. They've united a variety of other symmetric polynomials which arise as characters of different representations of different types of spaces. The polynomials themselves form a linear basis of the space of symmetric polynomials, so they're a nice thing to work with. I'm not going to give you a very explicit formula for them, because unfortunately there isn't. However, I'll give you the only formula that you'll really need for them, which is a defining property. And it's the property that they actually arise as eigenfunctions for a particular operator. In fact, there's a whole family of operators that they diagonalize, hence making them themselves an integrable system. But you define something, and this is what McDonald defined. It's called the McDonald first difference operator. It's an operator that acts on symmetric polynomials, though it's not obvious that it takes symmetric polynomials to other symmetric polynomials because of the denominator. However, it acts in the ith coordinate by multiplying by q. This was the parameter q. And then it prefactor involving t, and then one sums over all possible coordinates, I equals 1 through n. It is possible to show that under a certain inner product structure on symmetric polynomials, this operator is self-adjoint. Now, self-adjoint operators have eigenvalues and eigenfunctions, and you can actually compute the eigenvalues of this operator quite nicely. The eigenvalues actually take a very nice form as q to some number times t to the n minus 1, and then q to another number, t to the n minus 2, and so on. And in fact, one identifies or calls the eigenfunction corresponding to that eigenvalue p lambda. So p lambda is the eigenfunction corresponding to the eigenvalue in which we have descending powers of q, q to the lambda 1, q to the lambda 2, and so on. Lambdas form the partition. Okay, so this is a very inexplicit formula for these polynomials, but in fact it will be just as explicit as we need. These polynomials have a variety of other nice properties. So one which I will use is the fact that, of course, as eigenfunctions of a self-adjoint operator, they are orthogonal to each other. They're not orthonormal. So one defines a dual basis, q lambda, as p lambda over its norm squared. Okay, so the p's and the q's together form a resolution of the identity, and one can compute the simple formula for the reproducing kernel. They satisfy a variety of other nice properties, what are called Peary or branching rules. Peary rules correspond to the action of these polynomials under multiplication by certain elementary symmetric polynomials. And branching rules correspond to what happens when you specialize one variable to, say, be 1, the decomposition into symmetric polynomials. How is it that we use these polynomials? What do we do with these polynomials? Well, it was known since the work of, for instance, Okunkov in 2001 on Schur measure. It was known that one could generalize Schur measure. Schur measure involved Schur polynomials. One could generalize this and form what would be called McDonald measure. That's what I'm going to define. What wasn't clear was what to do with this, and I'll come back to that in a moment. So this is, in light of developments of the last 15 years, this of course is a very natural thing to define. This is called the ascending McDonald process. It's a measure, or the family of measures on interlacing triangular arrays of non-negative integers. So you just think of some nice triangular array. The lambdas at a given level, because of their weakly decreasing list of numbers, this is what I would call a partition. So it's a sequence of interlacing partitions, which is interlaced according to the way that the inequalities are drawn, or the way that the triangular array is drawn. I'll define for you in a moment what the measure is, but let me bring everyone back to something that is more familiar, because I know that this is not necessarily. Let me tell you a special limiting degeneration of this, which will be more familiar and maybe give you a way to put this into some framework. Think about random matrix theory. Think about what's called the Gaussian unitary ensemble, an n by n Gaussian Hermitian matrix with complex Gaussian off-diagonal entries and Gaussian on-diagonal entries, subject to complex conjugate across diagonal. Now this has eigenvalues. The eigenvalues will sit, there of course will be reals, they won't be integers, and they won't necessarily be positive, but they'll sit at some given points. Now, if I look at my matrix, and now I look at the n minus 1 by n minus 1 principal corner, and I look at the eigenvalues of that matrix, of that submatrix, then I can graph those eigenvalues, and they necessarily will interlace. There's a nice inequality that says that eigenvalues of minors will interlace. And you can continue in this manner and plot all of the eigenvalues. And you get a measure on a triangular array of non-negative, of just reals, interlacing reals. Now this array has a very nice property that's inherited from the Gaussian measure. So the first property is that the measure on a given level, let's say on the nth level, is given by the G measure. It's given by the van der Waals squared of the eigenvalues times a Gaussian term, e to the sum of e to the minus sum of the eigenvalues squared. Given the knowledge of the top level, given the knowledge of the eigenvalues of the n by n matrix, the lower eigenvalues are actually distributed uniformly over the simplex of interlacing triangular arrays. It's a beautiful fact that goes back to Weil. So essentially, once you specify the measure on one level, it's very simple to specify the measure on the entire triangular array. It's essentially by a propagation by this sort of interlacing inequalities. Okay? Now, McDonald measure is a far-reaching generalization of that. What I will do for you is I will define, using McDonald polynomials, I'll define a measure on the top level, or on any given level, k. And then you can propagate, it's not exactly uniform, but it's some sort of QT deformation of the uniform. You can propagate that measure to a measure on the entire triangular array. And I'm not going to explain the propagation, but it is some minor modification of some QT deformation. So how is the measure at level n, or at level k, on this partition? How is it defined? Well, what you do is you take the McDonald p polynomial, indexed by partitions. You take the polynomial corresponding to the partition at that level, and then you evaluate it at some collection of parameters, a1 through an. Okay? Now, as long as you choose the a's to be positive, it turns out that these polynomials themselves have nice positivity properties, and this gives you a positive answer. So for every lambda, you get a positive number. And likewise, you take the q lambda, and you identify it at a collection of variables b1 through bn. And as long as the b's are also positive, you get another positive number. So for every lambda, you get a positive weight. And these weights can be normalized. The normalization is quite simple. It's just the sum of the p lambda, q lambda over all lambda. So the normalization constant will, of course, depend on the parameters a's and b's, but this gives you a probability measure. And now you're thinking to yourself, oh great, you defined some measure, why do I care? You know, what's the point? Because people did know that this was a measure that could be defined. But what wasn't clear to people was why should you study this? You know, what's the point? And also, how should you study it? You know, you define a measure, how are you going to study anything about the measure? So what I offer to you is two answers to those questions of why and how. And this is work that was initiated with Alexei Bordy and myself in our work on McDonald processes. So the idea is itself that you try to translate the integrable structure of these polynomials. In particular, I'll emphasize the eigenfunction property, into nice probabilistic content of the measures on the triangular arrays, or the measures at a given level, which are described by them. So the first answer, which is to the question of why study these, is that we construct a collection of Markov processes on these on these triangular arrays. So you can think of the triangular arrays as almost representing a two-dimensional height function, and then we have evolutions on these height functions. Now you can define nice dynamics on these, which map you, if you start with one array, which is defined according to a McDonald process, and you evolve it according to the dynamics, you get another marginally distributed array, which is described by another set of parameters, McDonald process. So if you're interested in the dynamics, or in some marginals of the dynamics, then you ought to be interested in the actual measures that describe the configurations. The second thing that we do, which of course is in line with this idea of integrable probability, is that we show that you can use the structure of McDonald polynomials to compute averages for a rather rich class of observables. Okay, so this variety of developments, which are some of the people who participated are here and noted below. So let me illustrate the probabilistic content a little bit more. Here's a little bit of an overview picture. Of course, not everything in this picture, not every problem that is related to these areas has been solved by McDonald processes, but certainly there's been some consequences. So McDonald processes sit on top. This is actually a picture which is grafted onto the structure of symmetric polynomials and the hierarchy of symmetric polynomials, where McDonald polynomials sit on top. So there are various degenerations I won't talk about, one being to the Jack polynomials, or general beta random matrix theory, also random matrix theory for finite fields. Various types of measures related to these and various quantities can be studied by the methods I'll explain. What I will go a little bit more into depth on in a moment is the connection, the limit. Well, when you set t is equal to 0, you get a relation to q k-sub. And then if you further take q goes to 1, you get a relation in this realm of Whittaker processes to the directed polymers that I was talking about earlier. Schur processes, and in fact, all of the determinantal models sit at the bottom of this picture. So basically everything sitting above Schur processes is no longer determinantal, and this is one of the techniques that we have to study them. Okay, so let me try to illustrate the answers or something behind these answers to why and how. Okay, so to answer why, let me actually explicitly construct for you or show you one Markov process which preserves McDonald measure, which I think you might be interested in. So here I've stepped down one level. Of course, the construction works at the higher level, but it's a little simpler what you get here. So you imagine a triangular array of particles. Each particle has a little exponential clock. And the clock rings, and it rings at a rate which is modulated by the distance between the particle and three of its neighbors. Its left, its bottom left, and its bottom right neighbor, the horizontal distance. Okay. And then you run this. And you can run it, for instance, from a packed configuration, which is a very degenerate case of a McDonald process, in which all the parameters are 0. Now, as you run this, you notice something, which is that, in fact, the leftmost particles of the system don't actually depend on anything but the leftmost particles of the system. All the arrows here imply that. So if you look marginally, the leftmost collection of particles itself is a Markov process, and lo and behold, what is it? It's q k-sub. So one basically drops two of the terms here, and you get 1 minus q to the distance. That's actually how q k-sub came about. That's how we discovered it. And one gets this essentially for free out of the structure. This comes out of what's called the Pierre rules from McDonald polynomials. There are other interesting processes or other interesting dynamics that preserve these processes, which I won't go into, however. Now, once you've made this connection to q k-sub, how can you answer the second question? How can you compute something about q k-sub or about the process? Well, the natural thing to do is a very simple idea, which will seem familiar to those who study things like 2D Ising model. If you can compute an expression for a partition function and you have operators that act nicely with respect to the elements of the partition function, you actually get a way to compute stuff about the measure itself. So let me assume that I have an operator, which I know at least I have one of, the McDonald first difference operator, which is diagonalized by the p lambdas, and the eigenvalue little d lambda. Now I take my partition function, my normalizing constant, pi, and if I apply the difference operator in the a variable, all that will happen is by linearity and then by this relation, is I'll just bring down a little factor of d lambda. So in reality, applying the difference operator to the partition function computes a weighted sum of the eigenvalues with respect to the weights, such that if I subsequently divide by the partition function again, I will have done nothing but compute the expectation under the McDonald measure of my eigenvalue. So it's like computing, expected pair expected magnetization, expected pair spin correlations, this sort of stuff from partition functions in Ising models. And luckily for us, even though the p lambda and the q lambda are quite inexplicit, the pi lambda has a very nice formula. This is called the Cauchy-Littlewood, or the Cauchy identity. The d lambdas are terribly explicit, and as are the capital D lambda, or the capital D's. So without any explicit knowledge of the measure, you get explicit formulas. And in fact, you get enough formulas to characterize the measure. In the case that I was studying of t equals 0, the eigenvalue simplifies. And you just get an eigenvalue of q to the lambda n. Or in other words, q to the location of the nth particle in q tesa plus n, which was the observable that we started out with in the beginning of the talk. So here I give you a way to compute expectations. Of course, I can take powers of the d and I get powers of the d lambda. So I get a way to compute all of these expectations in terms of these McDonald difference operators. Now it remains a little bit of work to translate the difference operators into integrals, and this can be done basically via residue expansions. So there's a natural way of rewriting these difference operators as residue integrals. Okay? So this gives you one proof of this result. Now, of course, this result, it went through some pretty hard machinery. And one would hope this is a very simple system. The formulas are relatively simple. The observables are relatively simple. One would hope that there is, perhaps a fortiori, a simpler way to prove this result, or a simpler way to perhaps even get at this result. Of course, if you only focus on q tesa, you're missing part of the picture. You're missing the whole triangular array structure. But maybe we can still persevere. So I'll describe to you very briefly the other approach, which is through quantum integrable systems. And from the beginning, it will seem very ad hoc, but in a moment I'll explain how it can be put on a more algebraic basis. So here is the ad hoc observation. Let me define the expectation, which I've been talking about the whole way along. Let me define this as a function vt and then n1 through nk. It's a deterministic function. Okay? Now, there is an observation, it's not very hard to make, that this function, deterministic function, satisfies a closed system of triangular evolution equations. In other words, the time derivative of v is equal to a certain triangular operator applied to v. In fact, the operator that you're applying here is the backwards generator of another very nice Markov process called the Q-boson system, which is illustrated here. It's a zero-range process in which particles jump to the left at a rate given by 1 minus q to the height. Now, it is possible that one just plugs in the formula I gave you on the last slide, the right-hand side. It's possible to check that this satisfies this. And by uniqueness of this triangular system, this implies that this is a solution, and it proves the theorem in a very short way. However, as I said, it's ad hoc, because from the beginning, why would you have studied q tesa? And for instance, why would you have studied this observable? And then how would you have guessed the formula to check? Okay, so this can all be put on a much less ad hoc basis by appealing to the theory of quantum integrable systems. So this is a theory which, in a sense, goes back to the work of Fadeev. It was prompted by the study of two-dimensional lattice models and 1 plus 1 dimensional spin chains. And the basic premise of it is that one finds solutions to what's called the LLR, or the Yang-Baxter equations. And from these solutions, which ultimately were put into a framework by Drinfeld of quantum groups, one is able to construct integrable or exactly solvable models whose transfer matrices could be diagonalized by a beta ansatz. Now, things are much more complicated when you deal with a finite lattice. If you go to an infinite lattice, things simplify incredibly. We've developed a variety of tools on infinite lattice, such as QPASAP or ASAP. In particular, let me mention one work that we posted a few days ago, in which we look at the asymmetric six-vertex model and we consider the stochastic transfer matrices, which is a certain special case. And we can use this to also produce for us nice integral probabilistic systems. So things like QTASAP arise from this manner of quantum integral systems, and the analysis, the tools that we have, the eigenfunction decomposition to solve the backward equation that one gets, also comes from this sort of machinery. One does need to prove a completeness of the beta ansatz, and this is something that we've been working out in various cases. Okay, let me, as time has come to an end, let me simply conclude. The idea that I wanted to get across to you over the course of this talk is that integrable probabilistic systems provide you with a means to both expand as well as refine your understanding of universality classes. They, just like the Gaussian distribution was first discovered through exact formulas, so true is it that these KPZ and various other universality classes have first been discovered through these approaches. Now, in their essence, since they are ultimately very exact, they need to originate from certain algebraic structures. So I described to you the role that symmetric functions, particularly Macdonald polynomials, play, or one role that they play in this theory, as well as very briefly the role played by essentially quantum groups or algebraic beta ansatz. All of these, of course, can be developed further, and we've only started. The key then is to develop ways to bridge the gap between the algebraic structures and the probabilistic systems, ways to compute meaningful quantities and to introduce meaningful or discover meaningful systems. In particular, we've found ways to both discover and analyze these systems in various cases. Here I focus primarily on the KPZ universality class, though there are many other directions to go and many other questions that one wants to approach. So ultimately, we are still at the de Moivre-Laplace stage. Universality so far has evaded us. There is, of course, work on universality of some of the models within the KPZ universality class, of the KPZ equation, stuff of that sort. But real universality of the KPZ fixed point is something that to date eludes us, and we continue to try to expand at least our understanding of the class itself. And this is where I'll end. Thank you very much.